Welcome to the third and final video of section 2.3, and realize what we're going to be dealing with today, or this particular video, is that we are going to look at how can we prove a limit statement and how can we use the definition of a limit in order to determine some real-life applications. And so we're going to begin with number 6, which states the limit as x approaches 3 of 3x squared minus 8x minus 3 all over x minus 3 equals 10. Now, by looking at this, we can get several things. For example, we know x sub 0 equals 3. We know that f of x is equal to 3x squared minus 8x minus 3 all over x minus 3. We know that the limit is 10. Now, how can we use the definition to prove this? Well, the first thing we need to do is we need to find some sort of an epsilon. And I'm just going to create my own epsilon. I'm going to let it be 0.01. And so, if our limit normally is 10 and our epsilon is 0.01, then we can put 10.01 there and 9.99 there, and we can determine the appropriate values. Now we know that, or we are going to assume that x sub 0 is 3, and so we're going to have to find delta. And if we can find a delta where this works, then we have proven that the limit is true. And so we are ready to actually try the first value, which is 9.99. And so let's go. 9.99 equals 3x squared minus 8x minus 3 all over x minus 3. Multiply both sides by x minus 3 and we get 3x squared minus 8x minus 3 equals 9.99x minus 29.97. Now what we're going to do here, we're going to subtract 9.99x and we're going to add 29.97, and we get 3x squared minus 17.99x plus 26.97 equals 0. And if we plug this into the quadratic formula, x equals 2.9967. It also, so x equals 2.9967. And then we can do the same thing for the 10.01. 10.01 equals 3x squared minus 8x minus 3 all over x minus 3. Multiply both sides by x minus 3. And that equals 10.01x minus 30.03. Now once again, subtract 10.01x and add 30.03 to both sides, and we get 3x squared minus 18.01x plus 27.03 equals 0. And once again, we can plug this into the quadratic formula to get x equals 3.0033. Now, once again, all we have to do is find the deltas. Delta sub 1 would equal 3 minus 2.9967, which is 0.0033. And delta sub 2 would be 3.0033 minus 3, which is 0.0033. And so delta equals 0.0033. So far it hasn't changed, except now, how have we proven it? Well, yes, we have determined a delta. such that all of that other business that is given in the definition is true. We have a delta called 0.0033, or have the value of 0.0033, and so we have actually proven that that limit statement is correct. Now, the final example, example number 7, does ask what is called a tolerance range. Now, a tolerance range, we're asking what's the absolute smallest value, what's the absolute biggest value that we could get. And so that's what we're ultimately looking for. But realize that the way it's stated may not be quite so simple. We are told in the second part of the problem that the absolute value of a minus 10 has to be less than 0.01. Now let's see what we have in those spots right there. First of all, we would have a. A represents f of x because that's the function that we're dealing with. So this is equivalent to the absolute value of f of x minus, well, this is the limit that we want it to be. This is the perfect area that we want, and it has to be less than, if we look at the definition, epsilon. So it becomes pretty simple. F of x is whatever a is, and a in this case is pi d squared over 4. L in this case would equal 10. Epsilon has to be between, or has to be at 0.01. So let's see what we get with our graph. We know our limit is 10. We can go up or down by 0.01. And just like always, we need to find the appropriate value. Okay, now the question becomes, what goes on right here? Well, nowhere is it given. But absolute perfect would mean it equals 10. So we could easily calculate 10 has to equal pi d squared over 4. We'll multiply both sides by 4. Pi d squared equals 40. Divide both sides by pi. D squared equals 40 over pi. And then take the square root of both sides. So that d would be approximately equal to, what, 3 point, well, you know what? This really isn't necessary because we need the range. We need from the high to the low. So the actual value really doesn't matter. But just for completion's sake, this is going to be somewhere around, what, let's see, the square root of 40 divided by pi is 3.568. So the perfect cylinder would have a diameter of 3.568. Not that that was necessary, because what we really want is we want the absolute minimum and the absolute maximum. So all we really had to do was calculate these. We don't need to calculate this intermediate step, but for completion's sake, it certainly didn't kill us. Okay, so next one, I'm going to try and find the minimum here. 9.99 equals pi d squared over 4. Multiply both sides by 4. Pi d squared equals 39.96. Divide both sides by pi and then take the square root of both sides, so that d would equal approximately 3.566. Now the only reason we have to really worry about the minimum and the maximum and not the actual value, the x sub 0, is the fact that we just need, if you look at the problem, we need a tolerance range of d. In other words, we need the d minimum and the d maximum. So I found the minimum. Now it's time to find the maximum, which will be when the area is 10.01. So 10.01 equals pi d squared over 4. Multiply both sides by 4. Pi d squared equals 40.04. And divide both sides by pi and take the square root of both sides, and then we get approximately 3.570. So to finally answer the question, what is the tolerance range? Well, we can have 3.566. The diameter has to be somewhere between there and 3.570. And that becomes the tolerance range.